What is a Taylor expression? Suppose you have a function f of x. Let's define fx is a function that is nth differentiable. That means you can differentiate nth time, or you can say we can differentiate this function as a n plus 1th time, n plus 1th time over an interval a comma b. Okay, that is our first definition, first statement. Now it is continuous and differentiable. Okay, continuous and differentiable, done. And we want to create, or we want to generate an approximation over this function with a polynomial Pn of x. It is our nth degree polynomial. Nth degree polynomial. Okay. What is the meaning of this nth degree polynomial? That means if we say second degree polynomial, that might be P2 of x. It is an example. Ax square plus bx plus c. So nth degree polynomial must be Pn of x. We can define in this way: a0 plus a1x plus a2x square and so on plus an x to the power of n. So this is our idea of these properties. Okay, so we have a function. That function can differentiate up to n plus 1 times. That means if f dash, f double dash, f triple dash, and so on, f n plus 1 derivative exists. That is exists. Okay, so now we want to approximate this function with this polynomial, that is our nth degree polynomial, that, and we want to say fx is approximated to our Pn of x, where we can take where f r of alpha is equal to P r n of alpha, where r is the order, oh sorry, not order, it is order, my bad, it would be order of differentiation. Okay, easy. Now, so this is our idea of Taylor's series. So we can write this fx in this way. Fx is our we can write as p, okay, not necessarily Pn of x. We can describe fx in this way. Let me remove this one. So in a differentiation, then we can express fx, that is our f alpha plus, that should be alpha, plus f dash of alpha plus x minus, here should be x minus alpha, my bad, f dash of alpha multiplied with x minus alpha, sorry, x minus alpha plus x minus alpha square by 2 factorial f double dash of alpha plus x minus alpha cube by 3 factorial f triple dash of alpha, it should be alpha, plus x minus alpha to the power of 4 by 4 factorial 4 of alpha, and so on, plus the last term should be our, and we can continue in this way. We can write here x minus alpha to the power of n by n factorial fn of alpha plus dot dot dot. Okay, this is our Taylor series expansion for at x equal to alpha, where alpha is belongs to over the interval a comma b. That is our Taylor series expression. Is it okay? Now we will now discuss, these are just basic idea, but mainly in this class we will mainly discuss about Taylor's approximation or error bound. What is the meaning of error bound? First of all, we have to understand what is error. Error is a difference between the actual value and the actual value and the approximated value. Okay, so whenever we write error, E is the difference of E actual, or you can write E actual minus E approximated, or I can say E practical value. So E actual minus E practical. That is our difference. And if we say mod of E, that will be our absolute. So this is our error. It will be our absolute error. Absolute error. That should be our mod of EA minus EP. And then we must have relative error. Mainly we are defining relative error in this way: ER EA minus EP by EA. And most probably most of the books defined this EA in this way: delta E by EA. That is our relative error. Relative error. At last, then we have percentage error. What is our percentage error? Percentage error is E percentage, that is delta E by E absolute value multiplied with 100%. That is our percentage error. Now, what is EA? Absolute, not absolute, actual result. You can write as a actual result, or you can write you can write actual result. There is no issue about that. Or you can say exact answer. Exact answer. Okay, and EP, that is our practical result or approximated result. Approximated result. Sounds okay? Now, so now this is a proper definition of error. Now, when we discussed about Taylor series, we said a function fx, and we tried to approximate this function to a polynomial Pn of x. Correct? So this is an approximation. That is not an exact result. So there must be an error. So we are defining that error as a En, that will be absolute En mod of fx minus Pn of x. Now look closely. Fx has n plus 1th derivative, right? Sorry, it should be derivative. Derivatives. N plus 1th derivatives. That means we have f dash, f double dash, f triple dash, and so on, f n plus 1. Correct? And Pn is a polynomial. Pn is a polynomial of degree n. Correct? So we must have Pn, Pn dash, Pn double dash, Pn triple dash, and so on, P nth derivative, and nth derivative of this one, Pn n plus 1. Now remember that whenever you take a second degree polynomial, let's say a x square plus bx plus c, so the third derivative of this second degree polynomial, that means p3 of that should be equal to 0. Now if we take third degree polynomial, then p4 of 3 of x must be 0. So you can say that Pn of x, it must be 0. Okay, so we have Pn, Pn dash, Pn double dash, all the values are there. So we don't need to approximate for any one of them. We have to approximate with, so we can say we don't need to approximate for them also, because they are equal. So we have to approximate for this portion. So the theory says that this modulus of En, that is our f of n, f of x, fx minus Pn of x must be less than equal to m of n plus 1 factorial by x minus alpha, not bracket, to the power of n plus 1. Okay, so what is our m? M is the maximum over the function n plus 1 of x, such that x belongs to the interval a comma b. What does it mean? At first, we will discuss about this portion. What does it mean? So we are accumulating all the elements, all the values over all the functional values over the interval a comma b. Okay, and the function is our here f n plus 1 of x. So we are collecting all the functional values over the interval, and we collected in a set, and m must be maximum of them. Okay, so let me describe in this way. Suppose it collects 2, 3, 4, 5, 7. So the maximum value, it should be 7. So m must be 7. That is the idea of this concept. Is that okay? Now, so this is our error bound. This portion is called error bound. Okay, what happened? This is our error bound. Now let's see how we can derive this one. So we have an idea that we have a function fx, and we tried to approximate this function over Pn of x. There is an nth degree differentiation. So for nth degree differentiation, that means whenever we differentiate f dash of x, that is equal to p x. In that case, you can say the error en of x, that should be 0. E dash, you can say f double dash of x, p n double dash of x, that means e n double dash of x, that must be 0, and so on. Now look closely. F nth derivative, so f n of x, that is equal to p n of x, and e n of x, that must be 0. Correct? Okay. So what about now? You know that p n plus 1 of n of x, that is equal to 0. So this functional value must be, okay, what is our x? X is a point. Okay, x should be not, x is a point, not x is alpha here. Okay, x is alpha. So at x equal to alpha, that is 0. Now, so f n plus 1 of alpha must be equal to e n plus 1 by e n of alpha, right? So you will get an error at n plus 1th derivative. Okay, now the function, it says that it is continuous and it has the n plus 1th derivative. All the derivatives are differentiable. What does it mean? It means it is continuous, right? It means it is continuous over a closed interval a comma b. A function which is continuous over a closed interval always bounded, and it is bounded above as well as bounded below. So it must be bounded. Bounded means the function f n plus 1 must have maxima, capital M, and minima, small m. Correct? So it has a maxima and minima. So for all, can we write in this way? Let's see. For our x over the interval a comma b, small m is smaller than f n plus 1 of x, which is smaller than capital M, and it is maxima, it is minima. M must be bigger than or equal to capital M, must be smaller than or equal to capital M. Okay, now m is bigger, so 1 is bigger than 1 is smaller than 2. So what about minus 2? Minus 2 should be smaller than 1, right? So with this idea, we can write here minus m should be smaller than m, smaller than capital M. Sounds okay? So we will write minus m less than equal to m less than equal to f n plus 1 of x less than capital M. Okay, I think it's okay. Perfect. Okay, now this portion. Now see, we don't need this portion. We don't need this part. So we just need minus m minus m less than equal to f n plus 1 of x less than equal to capital M, right? Now this f n plus 1 of x should be equal to e n of n plus 1 of x, right? Or you can say in this way, the maximum value is this. So the error must be belongs to over this interval. You can say in this way also. You can't directly say they are equal. You can say the functional value we are saying as a function over the interval a comma b, it has bounded, so the error must be bounded on this, right? So you can write m less than equal to e n plus 1 of x less than equal to capital M. Okay, now if we integrate over the interval alpha to x, because our point is x equal to alpha and we want to an arbitrary point x equal to x, so I want to integrate from alpha to x, m dx less than equal to e n plus 1 of x over the interval alpha to x dx less than equal to alpha x m dx. Now look closely. These are n plus 1th derivative of en, the error part. So en plus 1 is our n plus 1th derivative, right? Correct? N plus 1th derivative. So if we integrate en plus 1, so we will get back n of x, right? And also we have n of alpha, and remember that this alpha en of alpha is 0 at x equal to alpha, right? So we have minus m x minus alpha is less than equal to n of x minus n of alpha is less than equal to m x minus alpha. Okay, now so this portion, this one is equal to 0, this part. So we might have here minus m x minus alpha less than equal to n of x less than m x minus alpha. Now let's integrate once more. So we might x minus alpha whole square by 2 less than equal to, this part should be our n minus 1 of x, correct? And on our right side it should be m x minus alpha whole square by 2. So in the first term we can write 2 into 1. Here we can write 2 into 1. Now look closely. We differentiated second time, this power become n minus 1. If we differentiate n minus 1 times, if we integrate n minus 1 times, then this term should be m x minus alpha to the power of n minus 1 plus 2, that is n plus 1, and on denominator we should have n plus 1 factorial. Easy? Less than, this n minus 1 should become our en of x. Easy? And which should be less than m x minus alpha to the power of n plus 1 by n plus 1 factorial. So we got our result. Now you know that if we say that a is smaller than x, is smaller than minus a is smaller than x and greater than capital A plus a, so x mod x should be less than a, right? So we can write here modulus of en of x, the error term should be less than or equal to that m by n plus 1 factorial into x minus alpha to the power of n plus 1, and we just have to take here an approximate value. take an approximate value. So this is our error bound. Error bound. Error bound for Taylor series. Taylor series. And this error bound is known as Lagrange's error bound. Error bound. Okay. Now the last part, how we can work on this, how we can find the error for any function. So let's take an example. So we have a function, let's say fx, that is our, let's take an example fx, that is our cos x, and this function fx has been approximated over a third degree polynomial. Third degree polynomial at x equal to 0. Okay, now x equal to 0. Now you want to find the error for this part. Sounds okay, no? So you can find the approximate error for x equal to, let's say, 0.2. You want to find the approximation for x equal to 2. X equal to 0.2. So x equal to 0 is the approximate value. X equal to 0 where we find the Taylor series, and x equal to 2 at where we want to find the approximate error approximation. Is that clear? So x equal to 0 is our Taylor series expression. Taylor series expression. And x equal to 0.2, we have to find the approximation. So we can write en of 0.2, that must be, so third degree, so n should be 3. N should be 3, that is less than or equal to m by n plus 1, that means 4 factorial mod of x minus alpha whole to the power of n plus 1. Now what is our m? M is our cos x, right? M is our cos x, cos minus sine, then cos, then minus sine. Oh, it might be. Okay. So m is our maximum of fourth derivative of this function f4 of x for all x belongs to 0 to 0, 2. Let's take 0 to 0, 2. Make it shorter. Okay. Now, so what is our f dash of x? That is our minus sine x. F double dash of x, that should be our minus cos x. F triple dash of x, that will be our sine x. And f fourth derivative of x, that will be our also cos x. Now you know, over 0 to 0.2, the cos x is a decreasing function, and you will get the maximum value at x equal to 0. And what is the maximum value? Max, or capital M, must be cos 0, that is 1, right? So that error value, error part, E3 0.2 is less than or equal to 1 by 24 multiplied with 0 minus 0.2, that means 0.2 whole to the power of 4. That is our error. In this way, you can try to solve some of these questions. Let me know in the comment section if you have any doubt, so we can work on those questions. I hope you enjoyed this lesson. I will attach this problem with a PDF. Thank you so much. Just 1 second. Okay, what happened with this line? Thank you so much. Have a great day. Take care. Bye.